Hi, welcome to the new video. So, video will talk about Regmap apps maybe, which is a section layer in the Linux kernel, which works to access the various registers of the device attached to the various. In the last video, we referred to this IIO driver, where we understood what are the different terms, the different implementation details of IIO, how it interacts with the I2C, and it had the implementation of Regmap for the communication with the actual sensor, retrieving the data from there. So this video is in continuation to that. We try to understand what are the different components of the Regmap, how it gets tied to a particular driver, in case this IIO driver. But what I understand is it's not specific to a type of subsystem or a type of driver. It's basically more or less tied to a type of communication protocol Regmap supports. Basically, what I know is that Regmap has two different APIs to initialize the. Okay, we'll maybe check code or later stage, but yeah, Regmap basically it's we'll cover a couple of things. So we'll just list down what we are trying to do. So we'll cover what is Regmap, what is the Regmap, what is the Regmap, what is it, what is the core component, basically what are the core components implementing the Regmap, how do we interact with the Regmap, right? How to interact with the Regmap, because once we, for example, initialize it, there will be some ways by which we use it, right? So those will include some sort of various structures, APIs, and all different ways. And why it is useful, main thing, why it's useful, why it's basically got introduced. That would be interesting to know. We will also try to understand what it brings in top of a just normal communication protocol like I2C or SPI. What does the Regmap builds on top of that? And all of this thing will do it by reading some of the blogs which I have read so far line, and we'll refer to the blogs as well as we'll refer to the drivers that implements the Regmap. So in the last video we were referring to the one of the driver from magnetometer, so we'll still continue that, and with the same driver we'll try to understand the various Regmap implementation that are in the driver. So we'll use this ALS 31300 driver, which is nothing but a magnetometer, 3D linear Hall effect sensor, which we referred for IIO understanding. We'll continue with that, and maybe we'll take one more driver just to something new, just to understand the Regmap implementation whatever we discussed. Okay, so yeah, let's start. So we'll begin with the Regmap documentation in the Linux kernel. Now, one more interesting thing is there is no documentation such as we had for the IIO, right? We had a different pages which describes various concepts of the IIO, right? Here for Regmap, there is no such official documentation available on the Linux kernel documentation. So what we will do, we will refer the documentation which is inline in the code. So this is the regmap.h file, which is the main base file, header file, which needs to be included when you want to use. Cool. We'll try to cover this only as a documentation. We'll refer to the document, this comments, function headers and everything, that whatever they have defined, we'll try to understand. Now Regmap is basically, if you take from the data structure point of view, for a very simple Regmap interface, we need only two data structures. One is this Regmap config, which provides you, which is nothing but this is a structure that you define in your driver, which actually implements what are the different characters that your drivers will be supporting. Here what you basically will need is, you will define this object of this structure in your driver. You will initialize all these fields in a way where how you want your Regmap to work with your driver, what type of interactions your driver will support via Regmap, so that you configure within this config Regmap structure, and then you pass this Regmap structure to the initialization API, and as a return of that initialization API you receive a map, basically Regmap, on which you will perform all the operations. Okay, so I'll show you that in the driver. We'll open this driver, Regmap, right, the ALS 311300. Here if you look at Regmap config, okay, this is the driver, this is the main Regmap config structure, which defines how your Regmap will interact with the Regmap subsystem, what all features you want to support. So the basic, very minimal thing that you would need to define your Regmap structure is, what are the size of your register bits, like what is the maximum, what is the address length of your registers, basically how many bits each register is there, right? Some of the drivers supports 32-bit register, some of the drivers supports 8-bit. Normally I2C register, I2C based sensor is there, then it would be register bits would be 8 only. Now what is the size of the value each register will hold? Here it is 32 bits, so that means each register will have a 32 bits of values. So here normally it will be 8 in case of normal I2C. So what is the length of the register bits? How many bits are there in registers, and how many bits are there in a value of a given register, and how many total registers you want to access. So this is basically, you specify maximum address you want to access via the Regmap. So for example, if your device, I2C based device, is having 32 or 50, let's say, different registers starting from 00 to 50, you will provide 50 here. What it does is, basically whenever you do any operations on the Regmap, it will check whether the access that you are trying to do for a particular register, I2C register, that is valid or not, based on this max register. We'll discuss on this volatile later on, but the basic structure will contain these three things: maximum registers. You can avoid maximum register as well, you can skip it, but it's, I believe for a very foundational driver it should be there, just to be very clear what all register you are going to access, register bits and value bits. So you define your own structure with this, and when you probe your driver, basically, so this is the probe function of our I2C driver. Here we are doing the stuff of I2C and IIO. Here you will also initialize the Regmap. So how do you initialize the Regmap is, basically you use an API provided by Regmap as a Regmap init along with the protocol that you are working on. This particular driver is an I2C based IIO sensor, right? So you will use this API Regmap init I2C. It is just a resource managed function, devm variant of the function. Devm Regmap init I2C. It takes two arguments. One is the what I2C, basically the clients that you received as a part of your probe, basically your I2C client, which you pass to this Regmap, so that Regmap internally will know which particular device or which particular I2C device this Regmap is for, and the config structure that you have defined above. So basically this returns a map, another structure which you store in your device specific data structure. So in the device specific data structure, you have provided this structure Regmap map. You have created a pointer, and you are using this pointer to collect whatever return came from this Regmap init. Now whatever, this is the very basic thing, right? This is how your Regmap is initialized. You defined a config structure, you used init API to configure the Regmap based on your communication protocol, here it's I2C, and you collect whatever initialization return came as a one of the pointer, and you use all that pointer whenever you want to do read or write to that particular sensor. Simple, right? in case of I2C, if you would have done, so what you do in general I2C is that you do your I2C receive, I2C master send, master receive APIs, or maybe I2C transfer. So you basically use the I2C based API for each and every register that you access, right? Here you don't need to do it. What you simply do it, you use this use the define a regmap, the characteristic of the regmap based on the regmap config, and then you use that config to initialize your regmap, and you collect that to a structure regmap. Now whatever operation you will do based on that. Okay, now this was about initialization. Now the next thing is, how do you interact with the regmap now? Because you have done the initialization, what our final outcome should be is that we want to access the I2C sensors registers somehow, right? So for that, Regmap provides various APIs. So we'll refer to those APIs now. Okay. So this is one of the Regmap read API basically. We were in the header file, now we are in the Regmap read function. This is one of the API, very basic. For example, you want to read a particular register from this I2C sensor, right, via Regmap. So what you do, you simply call this function Regmap read. You provide input as your map Regmap. What register you want to read, you need to provide the address of that register, okay? And you need to provide a pointer to a particular variable in which you want to hold the value. So pointer to a store read value. So this will go, what will internally this will do is, it will directly go from Regmap and perform the I2C operation to read the particular register and store the value into this past reference and return it to you in this, and you will also receive the error code based on the result how this Regmap has performed. Nice. So this is one of the blog from open source for you, which it describes various APIs of the, it has as I said there, we talked about Regmap config, register bits, right? This is the number of bits the register of the device. For example, 1 byte register, it will be set of 8 bits basically. Value bits, how many bits can be there, we'll talk about this table and stuff. Max register, these are the Regmap APIs. Now this talks about various APIs. Regmap APIs declared in the regmap.h. The following are the important APIs. Initialization routines, we have used this, right? Regmap dev regmap init I2C. This, as I said, it supports SPI and I2C, so there is an equivalent API for initialization via SPI. So it takes SPI handler, the SPI device handler, and the Regmap config. Similarly for I2C, what we saw in our driver, we had this I2C client as a structure, and then the Regmap config. These are the two API, one for Regmap read and one for Regmap write. So if you look at this, those are having the same type of signature. It takes the Regmap as an input, first argument, the register that you want to read or write. If you want to read, you need to provide the reference so that the API can store the value into it. If you want to write, you simply provide the value which you want to write on this register that you have. Cool. Now it's simple, right? It has, so then now the question arises, if it was about that only, about writing and reading, it's much of overhead than a simple I2C. If it just supports these two things, but actually I2C this Regmap provides much more than the simple read and write. For example, you have something as you want to write multiple registers, from one range, basically a contiguous register from one address to the next couple of registers. Similarly, you want to read multiple addresses registers which are contiguous. So what you would do, you would use the I'll refer another blog here. So you use the bulk APIs. So this provides APIs called Regmap read, write. We used, right? We saw register address and the. Similarly, it provides Regmap bulk read and Regmap bulk write. So what it does, it takes an address as first argument is always Regmap. Whatever Regmap you are working on in your driver, that's the first argument. Then from where you want to read or write, then the array. For example, if you want to read, how many values you want to read, starting from this register. Okay, so write, how many register you want to write with this count, and the array from values from here and starting from this address. This is applicable for writing bulk registers which are contiguous in the address. For example, if you want to write 5 registers starting from 1, right, you can use it because you provide register address as a 1 and count as a 5, so it writes from 1 2 3 4 5 6. But you might also have something as non-contiguous addresses which you want to write in multiple register bulk, right? You have 10 register, but those are not contiguous. You want to write 1 2 3, then 7 8 9, then 15 20, like that, right? In that case, there is other set of APIs which does the writing of multiple bytes but with the non-contiguous addresses. Those are Regmap multi-register read, Regmap multi-register write. So it takes like this sequence, like you define an array of addresses. So these are the addresses that you want to write. One is 0x10, another is 0x28, and the values you have defined here. So if you are reading it, so what you do, you provide this array as a register addresses, and you provide this to hold the values into that array, basically. Now in case of multi-write, it could have been directly the same way, address and data, but they also provide one more important aspect is delay, because in read you could do the contiguous read as fast as you can, but while writing, some of the sensor expects it to be written at some delay in difference of some time, so that the sensor can do their initialization stuff appropriately. So here you get an optional parameter of write microsecond as well. So here you define the array, like in case of when you want to do a multi-register write, you define a register sequence. Now register sequence is nothing but having 3 value: the address, register address, the value to be written, and the delay up to which this register has to be written after that amount of delay. So you define register sequence like this. We want to write 2 different registers, one on 10 and one is on 0x28. So and the data is this one, right? You define register sequence with this size, and you provide address and the value. Similarly for another register, address and the value. Here, as I said, this delay value is optional. You are using it, you can provide, otherwise you can omit it. And you use the same API that you use similar to the bulk write. You use Regmap, sequence, and array size. Isn't it cool? Like you can do single register read and write. You can do multiple register read and write, contiguous as well as non-contiguous. Internally, it tracks or it maintains the communication on a given protocol, whether it's SPI or I2C. Error handling, everything is taken care by the Regmap internal. However, it would be using the internal APIs of I2C only, but it's everything is under the hood within the Regmap. Now the next level of use cases is bit level access. So in sensor registers, it's very common that each register holds different values in a single register with a different meanings. For example, I have a 8-bit register. First 3 bits is for some use case, next 3 bits are for something else, and remaining 2 bits are for something else. In that case, you need to do read and write on a bit level. For example, I have a register which is 8-bit long, and the lower nibble, which is 0 to 3 bits, are for a number of frames currently I am sending, and the latter 4 bits 4 to 7 holds the number of interrupt that the device has generated. So whenever I want to read or write these registers, I need to do a bit level access. So this particular API is Regmap write bits and write. I think there is a read bit also. It's update based. Check that maybe. Let's talk about Regmap write bit. So what it does, it takes the Regmap as an input, register address you want to write on. The bit mask, as I said, I have the requirement that first 4 bits 0 to 3 I want to write. So in case my bit mask will be 00001111, lower 4 bit, right? LSB side, and the value which I want to write. So what it will do, it will write the value, making bit mask and value as an AND on this particular register. It will simply go ahead and write it. That's what Regmap write bits do. Then what is the difference between Regmap write bits and update bits? Now that's interesting. Now when you do write, you do not check what is the current value of the register. You simply go ahead and dump your data into that particular bit mask, whatever value you want to write, positions. Whereas in the update bits, what this API does is, this API go ahead and first read this particular register address, whatever value it has. Then it checks whether the value which the currently it's there on this register address is the same as the bit value and mask or not. If it is same, then not need to write because it's already there. If it's not the same what we are trying to write, then it will go ahead and write it. So this basically here, in case of write bits, you are avoiding read. Here you are avoiding a write. But this is update bits is very useful in the terms, because generally what happens is that the register that we have on the sensor, right, are generally distributed based on these bits, as I said. So it's better to always change or modify the bits on which we want to operate on, not something that we like directly don't go ahead and just dump, and it might reset the different fields as well. So we should avoid that. So update bits is more frequently used compared to write bits. In case you are not caring what is there in the current register, you are simply initializing it, it's better to go with the write bits as well. But yeah, both are there. So we covered single register read byte, write byte, multiple read and write byte, contiguous, non-contiguous, bulk read and multi-byte, right? And bit level access also we have covered. Now we go ahead and check the reg fields. Now this is a little bit more deep concept, in terms of how you operate on a particular bits. As I said, right, I want to have only 4 bits to be used. So what I do, when I define a bit mask for that particular bits, and then I operate on it when I do read and write, and whenever I am working on the values. So the same thing Regmap also provides. So internally, if you want to have your Regmap to work on a particular fields only, right, you can do it. So here this guy has explained that there is a register, this one, in which he wants to operate on this 3 bits only, 4, 5 and 6. So he has defined a reg field like this. So what he has done, he has defined a reg field definition that in this particular register from 4 to 6 bits is for this particular RFPS, and he initializes that Regmap when he is doing that Regmap field. So here is a Regmap field allocation. So what he has done, he has provided a dev Regmap device, basically a Regmap and the register field he wants to, and he can use it RFP, whatever this Regmap field PS, whenever he wants to. So when he wants to read or write, he can simply go ahead and do this. He does not need to do that masking and everything, because whenever you have defined this reg field, you have already covered that within the definition, that what all bits you want to use. So this API takes care of masking and doing the ending and everything that is needed. Similarly to that, there are different APIs to operate on the Regmap fields. Clear bits, set bits, and hit bits, test bits. Yeah, this is basically for operate on the reg fields. The next part is register ranges. So what interesting feature this Regmap provides is that you know that you have n number of registers in the given sensor driver, right? And you can do any read and write to those addresses. I2C does not restrict you to do any read or write, even that sensor does not give the error on the I2C operation. But there is no check whether this particular register has to be read only, or this particular register has to be read write, or this particular register has to be write only. So you basically need to make sure that whatever you are doing, you are knowing what you do. So to overcome that, Regmap has something called register ranges. So what it does, it's basically allows you to define what all register have what kind of access on it. For example, if you have 20 different register, out of those 20 you have first 10 as a readable and next 10 as a writable. So you can define your register range in such a way that whenever you do a write on, for example, 0 to 10, which is read only, your Regmap will give the error that it's not allowed to write because this is read only register. Same way, if it is write only, when a read operation happens, your Regmap gives you an error that this is write only operation, you can't do the read on it, like that. How does it do it? So here this blog has given an example of different registers and everything, but the idea is very simple. How? There is now consider there is a structure which is holding which is called as a range. Now it holds two entries, one is minimum register and maximum register, because you want to define a range, so you need to know what is the start, the first register, and what is the end, last registers. And there is something called Regmap access table. So now you want to, whenever you define your range, what you need to define is what is the range, basically start and end address, and what type of access it is. So if I am, for example, I am defining a read only register, right? So what I do, I define something called a Regmap access table, like this. Okay, like this Regmap. I'll define a Regmap range. Okay, first, where what I am doing, I am defining the range, that what all registers are there in read range, because let's say let's assume I have first 10 register I want to define as a read only, right? So what I'll do, I'll define the range, Regmap range, like this. I'll call it whatever I want to give a name, and then I'll give the name as like Regmap range first address and the last address. Okay, then I'll create a Regmap access table, this one, and I'll give that range into the yes table. For example, yes ranges and number of yes ranges, and I'll give it, I'll initialize it like this. Now whenever I define this read table, I will simply put it, or sorry, assign it to the config that we talked in the very beginning, that this is the first how you want to have your Regmap to work, where you define your register bits, value bits, maximum register. There is one more entity called read table, write table, like that. So you are defining a read only, you have created the access table which takes the range and the size of the range, and you put it as a read table. So internally what happens when Regmap tries when you perform an Regmap read somehow for any particular address, Regmap internally go ahead and checks the read table, if read table is defined or not. Okay, it is defined, it goes and check whether the address that you are trying to read is within the yes range or not. Correct? So this is a good case, that you define what is possible in the operation. Similarly, if you define a write only, there is no change in the write, it simply changes where do you assign that access table entry. Here they have defined some register as a write only, right? So they have assigned that table, access table, to WR table. So it takes the range, yes, now the range, basically access table has two entity. One is yes range and no range. So this is about what you want to allow, and this is about what you want to restrict. Okay, so let's say if I want to have, as I said, I have 20 registers, first 10 are read only, second 10 to 20 are write only. So to make sure that only read only register gets read and only write only register gets written, I need to define yes and no ranges for both, and I need to assign read table and write table according to that. I hope this was clear. If it is clear, I would love to see in the comment that how will you define a read table and write table, having the first 10 register as a read only and next 10 register as a write only, defining the yes and no ranges. I would love to see that. So this basically, this ranges, right, your read table, write table, that stuff gives you a very interesting aspect, that you can also make sure that whatever registers that you are accessing are valid. When you define it in your driver, you know that it's not going to go wrong if you have defined it correctly. We will see that now there is similar to this, right, Regmap ranges for read and write. There is also something called volatile. So to understand volatile, first we'll need to understand what is caching and how does caching is supported by the Regmap. So what does caching means in Regmap is that, let's say you have 20 registers in your driver, in your sensor device, right? Out of those 20, as we said, first 10 are read only. Now those read only register could be something that out of those 10, only 5 is actually some register where device will modify those values, right? Rest 5s are just there and won't be modified by device. If you want to change it, it would be reflected somehow by writing the write registers, but the device won't change the last 5 registers, it will only change the first 5 write registers. So whenever you do the operation, what does this caching in the Regmap make sure that you don't do unnecessary communication over the transport channel to read something which is not necessary to read, because that are not going to be updated by the device. You want to make optimal use of the communication so that you have the best performance. So what you do, caching in the Regmap provides a way that it only reads for the things which are necessary. The first 5 register, if you perform any register access ranges from 0 to 5, it will, the Regmap will go and do a I2C or SPI communication and read the value from the device by performing the operation. Whereas if you do it for 7 or 8, which is ranging between 5 to 10 address, it won't perform an operation on the I2C. It will directly fetch the value from the cache which is stored there in the caching. This actually caching a little bit complex. I haven't seen much how does internally affect the performance, but this documentation somehow explains something like that. Now, as I said, caching is like that. So as I said, if you know that your register is not going to be changed by the device, you don't need to read it from the sensor. But there can be other side also. You want to make sure that whatever registers which can be updated by the device are read from the device directly, not something from the cache. So there comes the part of volatile. So what it does is that whenever you define a range, similarly you have defined a read range and write range, right? You also define the range for volatile tables similar to that. So what it does is that when you define a range, so similar to this RD table and write table we had read here, right? If you define it's based on the Regmap access table. Similarly for volatile also you define it like that only. You provide a yes range, for example, you define Regmap access table, call it as a volatile table, put it as a yes range, or maybe like this, right? And you assign it to, instead of assigning it to this thing RD table or write table, you assign it to the volatile table. I have defined here what is done. He has defined a range for volatile range. They have defined a range from one register to the next, and they have put it into the yes range, and they are using this table, access table, into assigning it to volatile table. So by doing this, what you make sure, what your driver in the Regmap makes sure, that whenever you perform an operation for this range of register, it will always perform an actual communication, retrieve the value from the sensor and provide it to you it won't use any cached value. So this is very useful while reading the data from the sensor, because in case of when we read the data from sensor register, the sensor itself has updated those values based on the readings that it has captured, and you are there to read those actual values, not something that was there styled in your driver which was received from the previous cycles. Here there is also a concept of synchronization bypassing. I haven't much paid attention to that. One more interesting point is these precious registers. Okay, so these precious registers are if you are aware of some of the registers in some of the devices, they call it as clear on read. Basically, as soon as you read it, the value will be cleared. So for example, there are in case of some of the microcontrollers, you would see that if the interrupt is received, once you receive the interrupt and you read the ISR, that register in which that to know what interrupt is, that value is resetted for the next iteration of the interrupt processing. So you have only one chance to read that. So in Regmap terminology, those register which are something somewhat gets cleared on read are called precious registers. Precious in a way that must be protected from accidental read. Only your driver has to read those values so that the value is not lost. Register value is not lost. So you provide those kind of register list as a precious registers, the way you provide it as a table, right? We had this volatile table, we have now precious table, where you define that whether that particular register is precious. Then anytime in your driver that value get read, it won't be lost. It will be there in read by precious table only. We'll go to the debugging later. We'll just go through the driver once, whatever we are looking, and try to map all these things. Okay, so let's first go and put our understanding into these nodes that we have made. Okay, what is it? So what is it is somewhat that what I understand is that it's an abstraction. Okay, abstraction layer on top of I2C and SPI for optimal use of communication. You don't need to basically go ahead and read, overdo stuff which are not necessary. For every register you do perform a I2C transfer message and do masking and perform an I2C operation, wait for the result and like that. So it's an abstraction on top of I2C or SPI which takes care of internals of communication base. Other than that, it provides you an abstraction where you can do a ranges, basically, by which that you make sure that you only use you have very good handling of what are read only registers are there, read only, write only, like that, and volatile registers. So this allows you handling of caching and what all performance speed has to be done more precisely. Core components, as I said, core components contains first of all the Regmap config. Okay, it's the main data structure which holds the how your Regmap should interact with the other, like how you want to define your Regmap. So it covers the size of the register, value of the registers, the, as I said, read range, right? Read table, write table, name. I think name, there is also for name. It also supports, we'll look at the driver, but it also similar to the providing the tables, right? It also supports something as a callbacks. For example, if I define a callback for read, so internally, instead of checking the whether the register address that you have specified lies within that range based on the table, it will call your callback which you have provided into the config, and you will need to define in that callback what is handling you what to give. So there can be your own API or callback you define in your driver to process on a specific callback. Then regmap config, other than regmap config, there is a regmap struct directly, so which is nothing but the return value that you hold from your initialization of the regmap. So the API that we call is this device was managed regmap init I2C or SPI, as I said. Based on the protocol your device supports, will call this. It will take the handler, whatever communication protocol, either it's I2C client or I2C API, okay, or the SPI will be SPI dev, SPI device node, and then the regmap config that we have defined will take the address of this. This will return to this struct regmap which you have defined in your device specific node, and you will use this regmap all over in your driver when you want to perform any operation on that. Next is how to interact with the regmap. Yeah, we have seen the various APIs to perform on single registers, multiple registers, okay, registers in bulk. We also have seen of the APIs for bits operation, right? Update bits and write bits. We did not pay much attention to reg fields, but it's there. It was not much to it, but yeah, reg fields are there. So there are different APIs to use it. Why it's useful, as I said, the way we have covered, right? It's something that it does not. It provides you a more in terms of feature that it makes use of the communication protocol optimally. It allows you to do the privacy, basically, that if it's read only, it makes sure that you accidentally don't write on those registers by providing the ranges and stuff. Cool. So now we'll go and try to understand this with the driver that we were looking at. Okay, so here coming to this point, this is the regmap config that we have defined. We are providing it to regmap init for I2C, providing the I2C handler, and storing it to this regmap. We'll just make sure that now we will see how we are operating on it. Okay, so what is they are doing here is they are reading basically. So here I just so in the previous video we understood, right, what will be this read row and the API, this IIO callbacks will be doing. So whenever you perform any operation on the sysfs entry of any row value, right, any row channel on the IIO, this callback will be called. When you do a cat sys bus IIO devices blah 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 in magnet row, like that, right? The row channel, when you read it, you will learn to this API, this callback. And what you are doing, you get some IIO dev structure, channel spec, and the value to be stored. When you read it, to provide it to again user space, you store this value into this. So what this API is doing, it is based on this mask and type of channel. It is actually going and calling this driver specific function, which is reading the data from the sensor. We have skipped this part because we were not aware of the regmap into much detail, but now we have, so we'll try to understand what these are doing. So now this is related to power management. We'll skip it. Here they have given a very good comment that loop until the data is valid. New data should have the ALS volume MSB data bit set to 1. Max update rate is 2 kilohertz. So we will wait for the 1 millisecond. So this is basically API defined in the regmap, which does a polling. Basically what it does, it polls on a particular value based on a condition, polls on a particular value, and iterates there with some delay for a particular given timeout until the either timeout is reached or the expected value has come. So what they are here doing is they are doing read poll timeout. They are using the regmap bulk API, okay, and these are the condition that they want to wait for, okay, and this is the time they want to try at every 20 microsecond. For how much time? 1 millisecond. So since their frequency is 2 kilohertz, that means every 20 microsecond they will have a new sample from the sensor. So they want to check every 20 microsecond that if the valid data is there. So what it does, their actual data lies on this particular when they do a bulk read. So bulk read actually is the API. Bulk read will take various input, right? Bulk read requires a map, regmap, on which it wants to perform the operation, from where it wants to read and where to store the data and how many data to read. So the API is provided here. The arguments to that API is provided here. Okay, so this is a map. Start reading from this value, store the data into this. This read poll timeout, what it does, it uses this API, keep firing this API at every 20 microsecond, and for every result it checks whether if there is any error or not. If no error, see if this particular from the buffer read on the first byte, if this particular bit is set or not, as they mentioned here, right? If it is set, that means we are good to, we have valid data. If not, try again. For how much time? Till you reach to 1 millisecond this timeout value. So once you bail out of this particular API, either you would have hit the timeout, so you return from here. If you did not hit the timeout, that means you performed the bulk read and there was some results. So you see whether the bulk read that was performed was failure or successful. If it was failure, again you return from here. If it is not failure, that means you had hit this particular condition. It is you had a valid data. So what you do, you use those macros that they have defined for that type of how the data is structured into the registers, and they get the value out of it and they use it. So this is the use of regmap bulk read. Now we'll talk about now they are using this this API for setting the bits. So what it does, basically in one of the registers there are few bits which configures the mode of the sensor. So they just want to update those bits only. So what they have done, they have used the regmap update bits API. We know it takes the first argument as a regmap, and which register to update on, and what is the mask of that register. Okay, we'll refer to that, and what is the value we want to write as which we have received in the operating mode API. Now if you look at this mask value, right, it will be sum of the bits. You see gen mask 10, which means first two bit 0 and bit 1, those two bits creates the mode of the sensor. So whatever value you have received in this API, either it will be 00, 01, 10 or 11. You will mask it with 0x last two bit as a 1, so 0x 3, and you write it using this regmap update bits. Cool. Now for reading, we can check in the driver whether we have regmap bulk read. We have seen, right, multi-read anybody is using or not. There is no multi-read API implemented in magnetometer sensor. Let's see if we have register read. Bulk we have seen, most of them are using bulk only. Page are there, write, read. Okay, write and read are there in this. These are single APIs, single register APIs basically. Okay, we'll open this. Sorry, I was open file. Okay, this is the register write. So what they are doing, taking the regmap as a first argument, the register address that they want to write and the value that they want to write. Similarly, there is regmap read. Okay, what it does, it uses regmap as the first API, first argument, the registry address that they want to read and the value to be stored in this temp variable, so that they have created here. Then they return it. Cool. So yeah, I think this was interesting. It was very interesting for me, at least, to understand how this Regmap works internally, as we bail out of using the various API specific to protocol, right? We can have a simplified way, simplified logic, which is irrespective of type of protocol it supports. You have a sensor of which supports I2C and SPI, you can simply define two different regmaps and use a core logic. There are multiple drivers ISO which is distributed like this. If it supports I2C and SPI both, they have defined they have developed the driver in 3 different files, where the core logic, the basic logic, lies within the core file, and communication protocol specific, which is defining the regmap and stuff, is specific to the protocol specific source file. This gives a very platform or a communication protocol agnostic communication way, where the core logic of how your sensor driver should interact, how it should handle everything, is the crux of everything, and you don't need to worry about manipulating the bits at lower level and do the stuff on your own. Cool. So yeah, that was all we wanted to cover in this video. Let me know in the comments whether there is something that you would like me to do to improve things which I do, or whatever you want to do next, want me to cover next videos. Thank you for being with me, and yeah, I'll put the links to these blogs in the description. You can go ahead and read through. Great. Thank you for watching.